Professor Anindya as the next speaker, and he'll tell us about twisted bilayer graphene, a magic platform.
First of all, I would like to thank Indian Academy of Sciences for giving me opportunity to present our work, which we have been working on this twisted system. And I would like to thank Manish for inviting me, and because of that I am here today. And please feel free to ask question, anything, please raise your hand. And yeah. So the topic I have chosen, so rather than giving too much our experimental data, I thought maybe I will give a overview about what is twisted bilayer graphene and why it's called a magic platform. And these works mostly I'll from these two papers and recently which is in archive, this one. And I would like to thank our previous speaker, Professor Mahadevan and Professor Ghosh, already introduced the field. It's much easier for me to go through this field, but still I'll keep some of the slide about the introductory slide about the field of this research. So the plan of my talk is following. I'll be introduce what is this twisted bilayer graphene and what is the big deal about it, and what are the experimental signature has been done, some broad aspect of these systems, and what we have been working using a transport coefficient measurement, which is one of them. In a transport you measure resistance or thermal conductance. Another important transport coefficient is called thermopower, and we use this unique thermopower to probe these systems. And the key question which I will be asking my talk, how thermopower can probe in the first part of the talk, how the interaction driven phase transition in these systems, and the second part is a many body correlation physics, how thermopower can reveal about the existence of the local moments in this kind of systems. So let's start. Why? First question: why twisted bilayer? Although previous speaker introduced the field, but still let's ask again: why twisted bilayer graphene? It turns out that before I answer this question, let's go over what we learned about in our basic physics systems. That we learned about basically two kind of system or three kind of systems. For example, metal we know, and insulator we have heard about, and semiconductors. And all this majority of these systems you can describe by single particle or the quasi particle descriptions. And we know that if the Fermi energy inside my band, in this case what you see in this cartoon picture, this is your energy and this is your density of state. And if the Fermi energy here inside the band where you have a finite density of states, the systems conduct, and that's your metal. On contrary, if the Fermi energy between the band inside the system, which is inside the gap, that we know a insulator or band insulator. However, last 30 years so we have learned new kind of insulator, and one of them, for example, topological insulator, which comes topology aspect, and that's a beautiful physics which is rolling over last 30 years, and still we have been working in this kind of system. Here in these systems you have a bulk gap, but on the surface there are protected states. So these are topological insulator. Not only that, there are again much more exotic, both are exotic, but where there are interactions or many body physics you cannot describe by now this single particle picture. You have to talk about like many body correlation physics, and that is something called correlated insulator. So in this cartoon picture what I have showed here, that this system in a single particle level, Fermi energy is inside the band, it should have given me metallic behavior, but in reality the system actually shows a insulator, and this is becoming because of the correlation effect, because of the correlation among the particle, and this is called correlated insulator. And today's talk mostly around this kind of insulator. And why this correlated insulator is important in this in solid state physics, you will see this is the again cartoon picture without going to details. What it shows that in this system, if the system is half filled, there is a language of half filled. It tells about that if the unit cell, if a unit cell is filled by half of the degeneracy, for example, in this case, if you have a spin degeneracy, and if you have each unit cell is filled by one electron, you can, that's your half filled condition, and that's your correlated insulator. But if you slightly dome, you have a rich phase diagram of your solid state physics, and you can have whatever exotic physics you like to have all this phase diagram can be captured in this kind of system. For example, this is your Mott insulator, and if you slightly tune, you can have a superconductivity, you can have a strange metal where the resistance change the linearity, even very low temperature to very high temperature limit. There are pseudo gap phase and Fermi liquid, the conventional phase. So what you see, that correlator insulator is sort of like a building blocks for example, this high TC superconductor and many more exotic phases. Now, why I am saying so? That is the answer why the twisted bilayer graphene. So let's try to understand, is there any single platform where you can whatever physics I said, correlator insulator, superconductivity, pseudo gap, strange metal, is there any single platform you can study all of the physics in a same platform? It turns out it's not easy, because most of the system it shows only one kind of characteristics, or you have to do up chemically, system may change and so on. And here is the graphene, which already my previous speaker already said how important is the discovery of graphene, this 2D material, by this Scott step technique. And we know that graphene is a single set of carbon atoms, and it has a many interesting physics. For example, single layer graphene has a Dirac-like linear dispersons, or for example bilayer graphene, which has a which can tunable semiconductor, you can open a gap by electric field. And however, in this mother-like single layer graphene or bilayer graphene, you don't see the many body correlation physics or strong correlation. What you see is a basically mean field kind of interaction, or mostly weak interaction physics, but you don't see like the strong correlation physics in the systems. And here comes this field which has emerged for last few years, specifically last 5 years, which is twisted bilayer graphene. As this picture shows, you take a 2 graphene sheet, and if you give a relative twist angle, what you create a Moire superlattice, and you can quantify the Moire superlattice in various way. One of the way you can define the Moire wavelength, for example, theta is equal to the 1.1 degree, the Moire wavelength is 12 nanometer, which is much higher than the original honeycomb lattice of your single layer graphene. Now, if you try to look at, this is your real space of your 2 graphene sheet. If you try to look at the called reciprocal space, you have a formation of mini Brillouin zone. And now in the systems, this is your real space unit cell. If you have to fill this band, which I was talking about, the language of half filled or full filled, if you have to fill a band of the system, you have to either fill by 4 electron, or you have to remove by 4 electrons. And this 8 electrons come because you have a 2 spin, plus there is a Valley degrees of freedom in this case, and there are 2 layers, so that gives you total 8 degeneracy in the system. So the point is, if this unit cell, the real space, if you have either you fill by 4 electron, you completely fill the band, or if you remove the 4 electron, you completely empty the band. So remember, yes, the 4 comes because you see there are graphene, original graphene, already there are 4 degeneracy, because you have a 2 spin and 2 valley. But here you can see there are 2 kind of mini Brillouin zone. One is coming from the K prime of the top and bottom layer, other is coming K valley from the top and bottom layer. So the layer degrees of freedom also important in this, because the 2 layer of this thing. So that is the reason you can show that this is actually 8 electron total required to fill or empty -4 to +4. You need this thing. So remember, this is the filling I will be talking about, because when I say filling, I will be talking about how many carriers per Moire unit cell. So okay, that's fine. So you can see at least the importance of the twisted this Moire unit cell. Then the next question comes: is there any importance of the angle? Right? Is there any importance of the specific angle, which I showed here 1.1 degree? Indeed, you need there is an importance of the angle, and it comes following, which you can argue in a hand waving way. Because your reciprocal lattice, your Brillouin zones are rotated by this twist angle. If you try to look at the energy dispersion of your, let's say, bottom graphene and top graphene, and these 2 graphene dispersion, they might be crossing point at particular energy, and that depend on what is your twist angle. Now, if they don't talk to each other, which is like there is no hopping, this will be like your the band structure of the system. But reality, we know that there is a electron hops between the top and bottom layer, or in other words, they are talking to each other. So this crossing point, they will hybridize, and we know that they will create a bonding and anti-bonding orbital. So once they hybridize, they will open a gap, and you can show that what crossing point is required that will make a flat band, because we know the hopping strength, which is 0.3 eV, that's the maximum hopping strength. By this argument, you can easily show that I need theta is equal to 1.1 degree to have a flat band without going to go any details calculation. So that tells you that exactly 1.1 is something special or something unique happen, which is known as magic angle in this kind of system. And this is this has been shown in a continuum model, and in fact there are many tight binding calculations which Manish and Co has Sinjon has and H.R. Krishnamurthy has been involved, even with relaxation and without relaxation. But the point is that original graphene, you have this linear dispersions which go large energy scale up to of the order of 1 eV. But in this 1.1 degree magic angle, you see there is engineering of the band, and you have a tiny band at the low energy, you can see completely flat band, and which is separated from this high energy dispersive band with a band gap. So that is the unique of the system, that you can give a flat band, where flat band meaning your energy is almost not changing with the momentum. Although you are changing the momentum, the energy is not changing, and you can see that the width of this band typically of the order of few tens of MeV. So, so this is a cartoon picture I have taken from Pablo's side, and this tells you how the band structure changes with the twist angle. As you can see that as you reduce the twist angle, the flat, the width of your low energy band, it becomes flat. And in fact, at magic angle, this is really become flat. Even if you further reduce, the band becomes a little dispersive, and so on and so forth. So okay, twisted bilayer, there is a flat band which is isolated from your dispersive band. But what is the importance of it? We know that if you make a flat band, the velocity is now very low, very small, and the interaction actually dominates. So in this system now, what happened, because of the flat band, your interaction to your hopping term become that ratio becomes more than 1. So in this case, you cannot now think about single particle picture. Rather, you have to talk about the many body or strong. The electron interaction becomes very dominant in this kind of system, and that was the that's the way this field started. Although McDonald predicted in 2018, 2011, the first paper came out in 2018, and they saw that this is unusual result, that although Fermi energy, this is a cartoon picture of the density of state of your twisted bilayer, but what you see, that they see many features in the conductance. First of all, Dirac point, you have a low density of state, your conductance is very low. Then you have this Moire gap, which is our previous speaker already told, that if you have Moire gap because of the zone folding, and you have again conductance goes to 0, that because there is no state. However, even the Fermi energy inside the band, where you should have a large density of state, but the conductance goes to 0. So that is the remarkable result, that that you are inside the band where the single particle density of state should have been maximum, but your conductance goes to 0. And this is exactly happen, exactly half filling of both sides. So here the filling definition, again what I introduced, the number of electron per unit cell. So 0 is the Dirac point. 4 electron per unit cell, you basically fill up the band, or -4 you make it empty. But the interesting point is -2 and +2, that you cannot describe by the single particle picture, and this is the way this the magic land of this twisted bilayer graphene started because of this work, and followed by there are many dramatic very exotic thing has been seen in a same platform, which the idea I was talking about. In a same platform, how can you have a you can have many interesting physics. For example, superconductivity, topological insulator, Chern insulator is like a H physics at 0 magnetic field. So you can even fractional Chern insulator physics. There has been orbital ferromagnetism, which coming again, the Berry curvature and so on. Quantum anomalous Hall, linear resistivity, almost T tends to 0 limit, strange metal, large electron phonon coupling. So many of all this exotic thing, what you would like to have in our condensed matter platform, you can have in this twisted bilayer graphene, where the twinning parameter is you can have a twist angle change, you can change the carrier concentrations or temperature, magnetic field, and so on. So now comes to our experiment. So many of these this emerging physics are related to the electronic band structure of the systems. And if I zoom this flat band, if you look at the flat band which I was talking about near your Dirac point, you have a low density of state, then you have a high density of state, your conduction and valency band. And many of these interesting physics, they rely on this band structure or the density of state. Now question is, how do you and not only that, there are unique feature of this electronic structure. What have been shown that this flat band has 4 flavor, which I was talking about, that are 2 spin and 2 valley, and more importantly, this cartoon picture shows that although you assume that if I fill the carrier, all the 4 flavors is supposed to be filled by equally, but in reality what happens when I fill the carrier, suddenly one of the flavor, here I have shown like a 4 glasses, you are filled by the water, but you know the 4 glasses is supposed to fill equally, but in reality what happened, one of the glass or one of the flavor get filled up, and this is because of the interactions, and this is sort of, you know, that tells you something, you know, important question, whether this band structure I am talking about is it a rigid band or a non-rigid band. Okay. So these are the important questions. So question is, how do you probe now electronic structures? You cannot do like a RPS measurement, which is angle reserve photoemission spectroscopy, because the device size these are mesoscopic, like micron scale, and the energy scale of the flat band I am talking about tens of MeV. You cannot do easily like a RPS measurement to know the electronic structure. What are the measurement technique people have used? Like for example STM, because STM you can measure tunneling density of state, and that way you can find what is your electronic structure. Or people have used capacitation measurement or compressibility measurement, which can give you thermodynamic density of state in the system. So these are the true probe, these are the measurement has been shown, and they also show some signature of that non-rigid band. It shows that the bands are actually not rigid. Once you fill carriers, the band actually keep changing. The way I was talking about that cartoon, the glass picture I was showing this thing. So that comes to our experiment, which we have been doing thermopower measurement to probe this electronic structure. So let's go what basic about thermopower. What is the thermopower tells about? Thermopower is like this way. Let's say this is your device. You create a temperature gradient, and what happens because of the temperature gradient, your carriers they will move from high entropic place to low entropy. So there will be deficiency of the carrier of this side, and there will be accumulation of the carrier. And for example, if the charged particles are electron-like, so this will give me a positive charge this side and negative charge. So if you have a temperature gradient across a sample, that will create a thermoelectric voltage. You might have noticed if this is an electron, if this is the carrier as hole type, this would have been different sign, because if the hole type, hole will migrate this to this side, so this will be positive charge, this will be negative charge. So you can see the thermopower is very sensitive to the polarity will change. So thermopower is very sensitive to what kind of particle also you are studying, like an electron or hole like, which conductivity or resistance cannot give you these informations. And the way you can define thermopower you characterize called the Seebeck coefficient, which is the ratio between the generated thermoelectric voltage divided by temperature difference, that gives you the Seebeck coefficients. And just to give you more overview, for example, and this tells you without going details, the thermopower is a highly sensitive to the particle hole asymmetry of the band structure. Just to give you physical picture, what does it mean? For example, at the Dirac point, you have a both electron and hole type of carrier, because that's a particle hole symmetric point. If you have a hot and cold, again, both electron and hole, they will move from hot to cold end, but this will not give me anything, because both electron goes from one end to other end, the resultant thermoelectric voltage will be 0. So this is exactly has been seen, that Dirac point thermoelectric voltage will be 0, but if you go to one side where the more electron light, so the thermopower will be in negative, and if you go to hole side, that will be positive. So the thermopower, the point is thermopower is very sensitive to particle hole symmetric. In other words, which is known, thermopower is proportional to the derivative of the density of state, whereas the resistance is just a proportional to the density of state. So you can see that thermopower is highly sensitive to your, so it can take about information about your band structure. So that comes to what is our the way we make the devices. So the way we make a device is called well-known technique called tear and stack technique. This is the this Pablo show us how to do that. So the way we take a single graphene sheet and we cut into 2 pieces, and we make a relative angle between them, because the single piece, because you have to maintain the same crystallographic axis. So so that's the way we make a twisted bilayer graphene. This is a cartoon picture of schematic how you make it. So this is the black part is one graphene sheet. Basically we cut in 2 pieces. We give a relative twist angle between them, and that's the way we make a twisted bilayer. And this twisted bilayer are encapsulated between boron, nitrogen, and so on. So let's go to the measurement now. So this is your device. You don't see the twisted bilayer because this is encapsulated anyway. This is an optical image. You cannot see these moire structures. What you see the color here, the protected boron nitride on the top, and so there are many contacts here. These are source drain, and there are you see there are some isolated lines. These are heater lines. You will see to create a temperature gradient. So let's see now the device response. So the way we measure, like a 2-terminal resistance measurement, a typical lock-in technique we use, and what you see, this is the response of our device. So this is a Dirac point at 0 filling, but if you fill by 4 electrons, so there is again a resistance peak. If you do -4, again you see a resistance peak. That's the band insulator I was talking about, the Moire gap. However, you see a resistance peak even at positive integer filling like +1 and +2, which you cannot describe by single particle picture. So this is definitely, this is coming from some correlation physics. So this is a one unique example of how the magic angle twisted bilayer graphene resistance response as a function of carrier concentration will look like. In fact, in this device we saw also left the whole side, the superconductivity dome also exists in the system. So this device turned out to be 1.05, and now let's so this is the resistance versus temperature. Again, it shows lots of interesting physics, but that's not part of the talk. Now let's do the thermoelectric or thermopower measurement. So what we do now, so as I told you, there is a heater connection here. So we pass a current along the heater, and that basically generates a temperature gradient across a sample. So you have a hot end and cold end. So we measure the thermoelectric voltage. So this is called well-known technique called V2 omega technique to measure the thermoelectric voltage, and also we measure a temperature difference because this experiment has to be done in a linear regime, and that experiment I'm talking about very low temperature, even 100 millikelvin to 1 Kelvin. So your the delta T has to be extremely small. So we have developed a technique called Johnson noise thermometry to measure the temperature. So the way we measure this temperature gradient by noise thermometry, and this is the noise thermometry data as a function of heater current. So this is the heater current. You are passing a current. It creates the thermoelectric voltage. You are measuring both of them simultaneously, the voltage as well as temperature. If you plot together, these plot for different gate voltages, but what you see, the V2 omega and delta T, they are increasing linearly. That tells you that you are in a linear regime, and the slope of this data they give you the Seebeck coefficient, and that if you plot, this is your thermopower or Seebeck coefficient as a function of carrier concentration of your twisted bilayer graphene. To just give you the band structure, if you have a single particle band structure like this, so what you see here, there are a few interesting points, that these are both conduction and valency bond is quite symmetric, and Dirac point thermopower 0, then there are another crossing, and you can see +4 and -4, you have another crossing because you are going from the flat band to dispersive band, and what you can understand qualitative level by the single particle picture there, because at the Dirac point you will have a particle symmetric. Similarly, near about the middle of the band there will be particle symmetric, and that will also the sign changes can be explained. And this is a classic example of thermopower in magic angle twisted bilayer graphene at 10 Kelvin. However, once you lower the temperature, there are some interesting things happen. And one of the things is that if you lower the temperature, you can see the thermopower at the integer filling. This is a filling 2 electron per mole in the cell. Thermopower actually gives you some kind of peak structure coming out. This is unusual. You cannot explain. I'll tell you in a moment why it cannot be. And we see that this, as you lower the temperature even less than 5 Kelvin, even this peak becomes stronger. So this is and these values are like 100 microvolt per Kelvin at 1 Kelvin. This is the highest reported thermoelectric voltage at this temperature level. Typically at this temperature level, typically the thermoelectric voltage is very poor. If I very low, if I tell you the mother graphene is like almost 1000 times or 100 times smaller than this value. So this is unusually very high, and this is anomalous because you don't expect the thermopower at peak at this filling 2, because the MOT, there is a famous MOT formula which tells you where the thermopower should change your sign. You can see the MOT is supposed to give you, this is your derivative of the resistance, the MOT is supposed to give you many changes in your thermopower features, but major thermopower you have only single crossing, so complete MOT violation. So at the resistance peak at the filling 2, you are supposed to see actually thermopower is supposed to go to 0. Instead of going to 0, it shows you large resistance, large thermopower. So this is a complete MOT violation. Not only the temperature dependence shows very unusual one, which MOT supposed to give you linearity, but this you can see the very non-linear thing. So in fact, same time, or in those groups also show that there is a in fact more violation, not in magic angle device, but away from magic angle also they see. And we see that if you go very far away from magic angle, 1.66 and 0.35, the mod actually value, there is no problems. So the way we understood, so that's the last slide probably, what we understood by mean field calculation, that the rigid band I was talking about, flat band, this is not true. Because of the interaction, what happened, this 4 flavor which is supposed to equally fill, what happened, one of the flavor it gets completely filled up and other flavor completely empty, and this happens at integer filling because of the interaction, and as a result this is supposed to be rigid band, but the non-rigid band gives you this kind of density of state which is sort of modulating and having a large particle asymmetry, and that is captured in our theoretical calculations, that can explain the thermopower, large thermopower peaks in integer filling. So let me conclude. Unfortunately, I will not be able to talk the second part, but what we have shown, the anomalous thermopower at very low temperature, like even less than 1 Kelvin in this kind of systems, and the giant thermopower at integer filling and complete mode violation, and one can understand at least mean field level in these systems that interaction driven quantum phase transitions gives you the large particular asymmetry, and that is the reason we see that large thermopower. So without going the second part, let me go to the acknowledged slide. So these are the students who has been, they are who are working hard work to get this kind of magic angle devices and all the measurements. This is our theoretical collaborators, and also we in-house, I always discuss many physics, Shinjon, Chris and Manish for many discussion about the twistor. Thank you very much for your attention.
Now, if your thermopower is so high at so very low temperature, if you could do such experiment at room temperature, would it be very good for applications?
Thank you very much for your interesting. So that was the second part. So this is low temperature, then there was an intermediate temperature. The problem is high, because as I told you, there is a isolated flat band, but there is a higher energy band. So very high temperature, the higher energy band also start contributing. So eventually, very high temperature, the system like a graphene like, because you cannot distinguish, because you don't see the physics of the flat band anymore. If it was an isolated flat band, that would have been, that is the my second part. In fact, some intermediate range, you can see the impact the physics of local moments. But very high temperature, because of this high band, the other bands, they room temperature, yeah, room temperature is because this is like a 10 MeV, so room temperature is sort of like 30 MeV, so it takes the higher band physics, and at least experimentally we see like a spectrum look like graphene spectrum, so nothing unusual. Unusual part is up to something like a 70-80 Kelvin. Beyond that, system behave like the graphene like spectrum, and that is makes sense because 80 Kelvin as the bandwidth of this flat band is almost similar range.
So you have a graphene which is perfectly symmetric structure. Now you put a second layer, and then you see that if you tilt little bit, that is 1 point something 1, then you get a flat region in the momentum space, right? Now this you call magic angle. Now if you keep on tilting, I was thinking that you will again get the magic angle somewhere, and if you get again, what will be the reflection in the higher order billion zone?
Right. So very interesting question. So in fact, 1.1 degree is the magic angle I was talking about. There is a second magic angle happen near about 0.5 degree. However, the bandwidth, the way it changes with the angle, that is much more robust near about 1.1 degree, in the sense that the change of the bandwidth near about 1.1 degree is like a shallow kind of change. On the other hand, the second magic angle 0.5 degree, the bandwidth changes quite sharply. Now what is the difficulties in real experiment? Because real experiment, there will be, although I am saying that there is a 1.1 degree I am hitting, but this is like an average angle. There is a called angle inhomogeneity in the systems, and typically the angle variations are 10%. Right. So the second magic angle, even the 10% variation of your angle variation will kill all the physics what we are looking for, because there the bandwidth changes with the angle is quite sharply compared to 1.1 degree. So the answer to your question, yes, there are magic angle is there for the second magic angle around 0.5 degree, but technically it is very challenging from the experimental point of view, because the bandwidth changes much sharper near about the second magic angle. Now coming to your Brillouin zone other physics, so I hope the physics will be similar, but I have to recall how the other dispersive band etc. changes, but I guess it will be very similar kind of physics because anyway these physics are this is a single particle, mostly you can express you can explain by the zone folding kind of stuff. So I think my theory colleague maybe they will better answer how the, but my gut feeling is that it will not drastically change the other bands, right? That's the question, right? Other other higher energy bands, right?
Here, so this is a slightly technical questions. You asked the noise thermometry, right? Measuring the temperature. So your system has to behave like a resistor. So what is the range of this resistance, and what kind of accuracy can you get in your temperature measurements using this technique?
So this experiment, so accuracy depend on so only thing unknown here the resistance and temperature, because we know the Johnson thermometry only is 4 kBTR, so only the resistance and temperature. Resistance very accurately known, this because we know the low frequency resistance very accurately known. Only thing is,
so what is that value?
Yeah, so the only thing is that because the noise and the noise you are measuring this excess noise, because you are hitting on top of some background noise, with the background noise is determined by not the thermal background but rather than amplifier noise etc. So it's require lots of averaging to get a data. So the accuracy depends on how long you are averaging. So this data which I showed you, each data we average almost like a few hours to get a decent data. So in this experiment our resolution may be of the order of 10 millikelvin, but there are other experiments like quantum Hall, we use this same thermometry. There we have gone less than millikelvin accuracy for even less than 1 millikelvin for delta T accuracy.
Yeah, and the resistance value?
So there the resistance are quantum, because in quantum Hall is
not here in your experiment.
Here typically so we characterize the systems around not exactly large resistance where the resistance are flat, for example few kilo ohm, like a 1 kilo ohm to 10 kilo ohm, let's say.
High thermopower, Anindya. Is it the bandwidth, which means the large effective mass, or what? What is the?
Right. So this actually this equation tells you how the thermopower should depend on.
This is part of the thermopower.
Right.
Coefficient.
Right. So I'm coming to, so this density of state of course it matters, but other than density, asymmetry of the density of state around the Fermi energy.
That explains Seebeck coefficient.
Right.
Not the S squared times sigma, which is what gives you.
No, I have not measured. I have not calculated.
When you say thermopower, I thought that's what you would mean.
No, I am not talking about ZT. I have measured
Not
only.
ZT.
Yeah.
The numerator of ZT is thermopower. Power by definition is S squared.
Okay. So maybe yeah. So language. Okay. So I have measured thermo. I would say Seebeck coefficient.
Just thermoelectric coefficient.
Yeah, Seebeck coefficients. Yes, that's true. Yeah.
So asymmetry is what you think will explain?
So that's the way we say that asymmetry of the density of
If
state.
the flat band is very crucial,
Yeah.
then it's the effective mass which is probably dominating the Seebeck.
That's like a density of state large what you are talking about, because effective mass eventually it will give a large density of
It's
state.
inversely proportional to its density of state. So, in fact, when you have a flat band, it's
Right.
in a very tiny region of the K space.
Right.
So, you effectively the number of carriers is not very large, right? Because you have to sum up. all
You have
the
full
K
Brillouin zone.
points.
You have full Brillouin zone. Same number of K
Brillouin
points.
zone of the folded, twisted graphene.
That's true.
Very
Milli Brillouin.
tiny.
That's true. Yeah.
Yeah, which is very tiny region close to the K point.
That's true. Yeah.
So, number of carriers is not so large, which is actually good for high Seebeck coefficient.
That's true. Right.
And flat band would mean large.
Well, that is not true because the same density, if you look at the graphene for example, at the same density, thermopower is extremely low.
Yes.
Right.
But that you don't have the flat band then. Flat band gives you the large effective mass. See, if you look at the phenomenological
Right.
expression for Seebeck coefficient,
Right.
it's directly proportional to.
But you
effective
cannot
mass.
use because the Mott formula is not valid here.
No,
Because in
that's
this
not
system,
Mott formula.
the Mott formula you cannot utilize.
That's not the Mott. This is based on Mahan's work, G.D. Mahan's.
I see. Okay. So what I am trying to say, the single particle picture actually cannot describe you need a correlation physics to describe this physics, and the point is the particle hole asymmetry, because even if you have large density of state, for example, I will give you the point, if you have large density of state, you have the Fermi energy here, if your particle hole asymmetric, the Seebeck coefficient still can be 0. Even if you have a large density of state at this point, because, right, even if you have large effective mass or large density of state, you do not have
correlations or not correlations. It's basically correlation function of entropic current and electric current.
Right. That's exactly right. Right.
Okay.
Right. Let's discuss that. It's very interesting.
I'm just interested in knowing whenever you are fabricating this graphene, I believe it can't be the ideal structure. Maybe you are getting just a pieces of graphene, right?
Yeah.
Is it true, right?
No, I didn't catch. So you are saying it's not the way picture I am showing, this is not an ideal system. That is true, as I told you that when I am saying 1.1 degree, but in reality there is a angle variation in my system. That's like a 10% angle variation. That's typically people have done by local measurements like STM or other measurement. People have shown that angle variation of the order of 10%. So that sense, this is not a exactly ideal system, the picture I am showing, but there is a, so 1.1 degree plus minus, you have an angle variation in your across the sample. That is true.
And how challenging it is to twist a layer, because it seems like
so
theoretically it seems very simple, but otherwise.
So that's the most challenging part, even though we are making a 1.1 degree, but you might have asked the question, is there any energy minima in the structure? 1.1 degree is the minimum energy, or reality the 0 degree is the minimum energy, because AB stacking, that's the Barnwell stack, that's the minimum energy. Other than that, there is no, people use this word called lubricating, lubrication, there is no energy minima. So that because of that, what happened, there is called relaxation physics here. So even you try to make a 1.1 degree, but the angle may turns out to be some different angle. So there is no, so at least there is no trick what we have found. The yield is like a 10%. If you make out of 10 devices, you have to just keep making the devices. But out of 10 devices, you will make a 1 device close to magic angle. So in our laboratory, so far we have hit at least more than 4 devices. I think that was my second part. So there is a, so these are the 4 near about magic angle device we have hit, but after making maybe 20 devices. So it's really, experimentally it's really challenging to hit. So that is not then twisted TMDs. TMDs even 2 degree, 3 degree, the flat bandwidth doesn't change much, and there are still you can interesting physics. But graphene is little, at least if you have to see the magic angle physics, you have to be close around the 1.1 degree, and which is very hard compared to TMDs.
So I'm just going to use another skateboard so that he can answer. We have 10 more minutes. So if you have any questions, he can answer as many as you want, and then we can end the session. It could also be for all the other speakers as well. Actually, this is a good time to.
So it's a very stupid question. So making that sample, you have to take the measurement immediately, or
no?
It can be stay in that particular configuration for.
That's very interesting question. So what I realize that relaxation I was talking about it only happened during the making the devices. Once the device is ready, ready meaning you land it, the contacts are defined. Even for 2 years, 3 years, nothing changes. The characteristic of the device, in fact, they are much more robust than the graphene sample, what we have realized. So it's a very good question. The experimentally, these devices are very robust. Once contacts are formed, you can go to low temperature, room temperature, many thermal cycle, nothing changes characteristics.
This is also a question which is easily asked, but not so easy to see whether it is possible experimentally. This magic angle is obtained at the, let's say, 3.5 angstrom gap between the 2 layers, right? That is the optimum gap. Is there a way that one can increase the gap a little bit more and see how this flat area changes?
Very interesting question. In fact, people have done that. What people have done, they use the pressure. So they have, in fact, one of the pioneering work when this started, so they use the pressure to tune the interatomic, the vertical distance, and see how the band structure changes. And in fact, by this, they are able to tune the superconductivity and many correlated features in this kind of structures. So using a pressure, indeed, people have done this experiment.
Can we go the other way around?
Increasing pressure distance, that is, I don't know, you have to, but hopping will reduce, right? Intercalating, yeah, something you can do. People have done
I
some,
see.
yeah.
Okay.
But not in the twisted bilayer. I think is there at least twisted bilayer not been seen.
The reason I am asking this question again and again is that we are familiar with graphene.
Right.
There is in the last 2 years bilayer borofene made, and bilayer borofenes have 202 electron bonds, some of them between the 2 layers. But its band structure is similar to monolayer graphene. Now, in borofene bilayers, if one can make a bilayer of this bilayer, it is possible to think of having 202 electron bonds coming out, because this is triangulines, not hexagonal sheets.
I see.
So it is possible that atoms come out of the plane in both directions, so that one have 202 electron bonds still having the standard 3.5, 3.6 interlayer distance, except for these additional occasional bonds, in which is localized.
I see.
So it is possible, if one goes away from graphene to another system, to adjust the interlayer distances in a similar picture. So that's what I was. Thank you.
Yeah, no, that would be fantastic. Yeah, but van der Waal, once they form a van der Waal, is a very strong interaction. You cannot change anything. In fact, they are very robust because the area is quite large. Unless this pressure experiment they have done this thing, or you can give some uniaxial strain and those kind of thing. But yeah, so the intercalation might be something can be done. But please go ahead.
Anindya, this is a follow-up of what Sankalpa asked. So basically, is it that when you anneal the sample, after you anneal the sample, because you do some annealing after you've done the twisting, right?
No, we don't. In fact, heating, we avoid heating.
I see.
We never.
Then
we
why
don't.
Is your device, then why does it, your device become stable after?
No, because heating meaning above room temperature, right? So usually this peak up and everything close to room temperature we do. So we never hit, like even we hit 50 degrees centigrade.
You mentioned.
So thermal cycle mean like low temperature to room temperature, not above room temperature. Okay. That is the image.
Why does, like you said, your devices were unstable when you formed them.
Yeah.
But once you made your contacts, your devices became stable.
Right.
So what do you attribute that?
Right. So first of all, once the device is making, there is some heating involved. Indeed, there's some 50, 60 degrees centigrade temperature involved, and that we feel is a culprit, because that is required because of the technical details. Otherwise, you cannot do all this pickup technique. So you have to some heat up is required. So that 50, 60 degree actually help them to relax. But some device, if it doesn't relax, let's say it's a statistical, some device maybe doesn't relax, and once it becomes room temperature, they're stuck. Now, once you form the contact, contact has a 1D bond, one-dimensional bond. So now you cannot move it, right? Because the contact has been written. It's like a constant from the end. So you can.
The entire thing clamped?
Yeah, it's like, see, you have some angle, but you have a contact now. Now you cannot rotate the relative angle because there is a support. The two rods are there, so you cannot. This is our gut feeling, and this is the way it is happening. That once this is landed, and you can do some preliminary angle checking by Raman. In fact, Raman can tell you whether you are close to 1.1 degree. This is we learned, and we can do that. That we routinely do. And once the contact is formed, we have seen many thermal cycle change room temperature to millikelvin. Characteristic doesn't change. It's quite robust in these devices.
Thanks.
Umesh also, yeah.
So Manish, within the single electron picture, are the states in the flat band localized on those ridges between the?
So it depends on which materials you're talking about.
Graphene, by
So in graphene, I think the electrons are localized in these
that
so in the
A. This is my second part.
So that's one way I would understand high Seebeck coefficient. If you remember famous work of Milli-Laser-Laus, which stimulated nanowires giving very high Seebeck coefficient. So you essentially have a network of nanowires in the bilayer system.
Absolutely. So that's a quite interesting. Yeah. So this localized. So in fact, the systems has a both character. You have a localized somehow and also some itinerary electrons. Yeah. So people are talking about now heavy fermion, this kind of physics. This was my second part where I was talking about these local moments, and you are indeed right that for that kind of local moment, there is a toy model you can use, and this kind of atomic limit calculations. You can do atomic limit Troy model, and indeed you are right that you can show very large thermopower for this system.
Think of these AA regions as a larger, I mean, it's a more
Right.
Network of wires.
Right. Network of
They're
wires. Yeah.
connected, but I think it's mostly that these are localized. The electrons are localized at these points, and they weakly hop. I mean, it's like think of this as the
No.
lattice.
In the flat bands, they cannot be localized at one site. I mean, unless you are looking at 1 year picture, the band states will be along those ridges which separate your AB and BA stacked sample.
Oh, you are saying the domain wall.
Yeah, domain walls.
The domain. Yeah.
Has someone looked at it, or?
I don't think it's localized. I think the effective picture that you can look at is that these AA regions form a Moire lattice. Form a lattice.
I see.
Basically, you can think of these.
So which is A in
This is the. So this, for example, this part. This is the AA part.
They form the lattice of these, and these are
I
weakly
see.
hopping between these.
Yeah.
Sir, if we take the graphene nitride, so similar twist angle will be there.
Graphene nitride. So what is this? So is it carbon and nitrogen?
Yes, alternate carbon and
nitrogen. That's an insulator, I guess. Of course, it has to be insulator, I guess. Graphene nitride is insulator, right? Some small, right. So, right. And you are saying between the some superlattice will be same structure. I mean, you will have a Moire superlattice which I was talking about.
You can exfoliate these sheets, graphene nitride. You can exfoliate them and make single sheets and sort of twist one with respect to the other. Is that the picture that you have in mind? That you can take one, for example, take it out, take this graphene nitride sheet and put another one on top with some angle. Is that the picture that you?
Yeah.
Yeah, you will get Moire.
Yeah.
Okay. Thank you.
But your starting is a band semiconductor. You have to look at now how the electronic structure will modulate.
Thank you, Anindya, for this long extended question and answer session.